Hello everyone, my name is Ethan Rodriguez and I'll be talking about my final project, Micron's stock trend classification and price prediction. For anyone that doesn't know, Micron is a company that produces all sorts of computer memory and storage devices. However, what they're mainly known for is their RAM. I'd like to begin by clarifying the purpose and discussing the motivation for my project. I'm going to introduce two different machine learning algorithms, naive Bayes and LSTM, and describe their processes and how they were implemented to predict Micron stock behavior. The main motivating factor for my project is a simple one. As someone who has a hobby in overclocking different types of RAM, I really enjoy overclocking Micron Rev-E DRAM and squeezing as much performance from them. Also, as an investor in Micron stock, I thought to myself, I wonder what would happen if I can predict the stock behavior, specifically the trend and closing price. Briefly, the outline of my presentation is as follows. I'll be defining and explaining the dataset I used, then I'll move on to the first method I used, which is naive Bayes with k-fold cross-validation. Afterwards, I'll describe the second method, which is the LSTM model. Finally, I'll conclude by providing some discussion about possible improvements to the models. The stock data I use is rather uncomplicated. The dataset is 1 year worth of Micron stock trading data from March 18, 2020 to March 17, 2021. It contains 252 rows with 7 columns. I excluded 3 of the columns as I wanted to forecast the stock based solely on 4 features: open, high, low, and close prices. Since there are no labels in the dataset for classification, I included a couple of labels, 1 and 2. These represent if the stock is down or up on a given day. So moving on to the first method, a naive Bayes model uses Bayes' theorem combined with making naive assumptions between the features. The naive assumption is that the features are independent of each other. I used k-fold cross-validation to evaluate the naive Bayes model. The procedure of the model goes as such. I randomize and evenly split the dataset using k equals 12 folders. For each unique folder, I select one folder as a validation set and take the remaining folders as training set. Then I implement naive Bayes on the training set and evaluate it on the validation set. Naive Bayes training involves finding the likelihoods via calculating the mean and standard deviation of all class features. That means a total of 16 parameters were trained in my project, and then afterwards I find the probability density functions via SciPy's norm function. Then I find all the priors and combine the likelihoods with the priors. And finally, I calculate and retain the average accuracy of the model. The results of the model: the average accuracy of one run with 12 folders ranged from 45.83% to 52.84%. And conducting 50 runs using the same number of folders, I get 49.91%. It's important to note that the naive Bayes model almost always classified the stock as down. Next, moving on to this more interesting part of the project, which is the advanced classifier that I applied. The advanced classifier I chose is long short-term memory, or LSTM. Actually, I shouldn't be saying classifier since I ultimately use LSTM for regression, but I'll talk more about that in a moment. A brief intro about LSTM. LSTM is a supervised, unsupervised learning method depending on how it's used. It's simply a recurrent neural network architecture where its cells are positioned in between the input and output layers of the neural network. And one of the main advantages LSTM has over other neural networks is its ability to keep or throw away data. What decides which data to keep and throw away, you may ask? Well, it has to do with how the LSTM cell is composed. An LSTM cell is composed of 3 components: input gate, forget gate, and output gate. And for each gate, there are sigmoid activation functions where its duty is to assign data as 0 to remove or 1 to keep. It's important that each gate has a sigmoid activation because it keeps the model differentiable. And since LSTM uses backpropagation, it needs it to be differentiable, which means chain rule needs to be applied, and all that pointing to the optimization algorithm that LSTM uses, which is a gradient descent. There's also hyperbolic tangent or tanh activation functions in the input and output gates. Their duty is to give weights to the values that are passed based on importance ranging from -1 to 1. These values multiplied with the output of the sigmoid function. Additionally, the tanh function is used to remove vanishing or exploding gradients that may occur when a large time step is present in an LSTM cell. So why choose this LSTM for stock prediction? Well, LSTM trains on time series data, and stock prices fluctuating are a form of time series data. So LSTM cells will decide the permanent closing stock prices over a certain amount of time steps, and the three gates regulate the flow of data. The procedure of my LSTM model, it goes as such. I use these packages from scikit-learn, TensorFlow's, Keras library, and Pandas. I first start off with collecting and importing the Micron stock data. I pre-process it with scikit's min-max scaler. Then I split with the data into training and testing sets using 70-30 ratio. I create, compile, and train the LSTM. My model architecture consists of 2 LSTM layers with 6 units and 1 dense, fully connected layer. The reason why the units are so low is because I'm using a small data set, and since I'm using LSTM for regression, I choose a variant of stochastic gradient descent, which is Adam. And the model trains with 35 epochs and a batch size of 12. Then afterwards I predict the test data and evaluate it with root mean squared error and mean forecast error. And then afterwards I predict the future 60 days and plot it. So my results are, after training 511 parameters, the loss function is 0.0015 and validation loss is 0.0046, and also the RMSE error for both testing and training sets are 78.25 and 49 respectively. Finally, the mean forecast error is 78.10. This is a graph of the closing Micron stock closing price. In blue is the original stock price. In red is the predicted train price, and the yellow is a predicted test. In this graph is the closing price of the last 10 time steps in blue as the actual closing price, and then in red is the prediction. As we see, there's a decrease in the stock, and then in this one it's just combining the last graph together on a normalized scale. So when I looked at these results, I was pretty disappointed because it doesn't look like the LSTM trained well at all. For instance, the difference in test and training RMSE is way too large, which implies some sort of over or under fit, which is what is observed in the predicted trained and test curves in the graph here. So yeah, it was pretty disappointing. But moving on to discussions and improvements for the naive Bayes. My inclination in improving the accuracy would be to increase the data set, let's say 10 times from 1 year to 10 years, increase the number of features in the data set, and then possibly apply PCA. While for LSTM, I would again increase my data set size. LSTM doesn't work well, I think, with too simple of a data set or too small. I would include trend deterministic data of the stock, such as momentum, 10-day moving average, and PU ratio, to minimize the loss function. And then I would increase the epochs and batch size. But overall, it was a fun project to do, and I got to play around with creating an LSTM model, which is, I think, pretty invaluable. These are my references, and thanks for your attention.